Perlu ini nggak sih on cam nggak ya?
Nggak usah deh.
Oke.
Yuk, kita record.
Okay. So good afternoon, everyone. So today we are going to present about our second progress report on aircraft design, DRO number 13, the Unmanned Piston-Propeller Cargo Aircraft. So generally, our second report consists of 5 chapters from the updates, general configuration, aerodynamic analysis, weight and balance, and then the structural layout. And then these are some updates on our aircraft design. So basically, our aircraft occurred an update in the design point due to some mistake we did at the magic jar estimation. So we have to decrease our wing loading from the initial wing loading 1300 Newton per meter square to only 1000 Newton per meter square, but the power loading is the same. So due to that wing loading revision, we have to enlarge our wing area. And then these are some updated general review drawing from our aircraft. The process design of wing and fuselage will be presented on the next slides. So starting from the wing design, we are going to present from the new wing area. We can obtain first the aircraft wing and airfoil lift coefficient in the cruising condition, and then we also have to obtain the CL max for the stall condition, and then we can select the proper airfoil, and then design the wing incident angle, dihedral angle, twist angle, winglet, and takeoff and landing distance, as well as the high lift devices. From the value of CL, we obtain the airfoil of our wing to NACA 4415 airfoil. We selected airfoil because it has a high lift coefficient and as well as good stall criteria. And then we design our wing based on our wing platform, and we can set up the incident angle to fulfill the zero angle of attack coefficient of lift, and as well as the other setting angle. And also for the twist angle, we twist the wing a little bit downward to make a good lift distribution in the span wise. And then the winglet, we can obtain a lower drag due to our additional winglet. And then these are our wing design, wing platform for the main wing and the horizontal tailplane. The next one will be presented by Bayu.
Okay, next I will explain about the fuselage design. There is no specific requirement for our aircraft because our aircraft is an unmanned cargo aircraft, but there is a cargo door that we need to define. The cargo door is 2 meters by 1.2 meters. Next one. We decided that the door would be 2 meters by 1.2 meters because it is big enough so that it can accommodate larger loads without affecting the structural integrity. There is also a fillet to add structural strength. It is positioned on the left side in front of the wing because it is the largest surface area that we can put the cargo door in. On the cross section, we can also see that there is a floor. The floor is just above the fillet of the fuselage, and under it there will be other components, but above the floor is all purely cargo area. Next.
And then this is the result of the aerodynamic analysis. The first one is the CL alpha estimation. The first one, the airfoil lift coefficient, we obtain it using XFR5 software. It can analyze the airfoil lift coefficient in a batch of Reynolds numbers. And then we also obtain the wing lift coefficient using the same software. And then for the whole aircraft configuration lift coefficient, we use .com software, as well as for the high lift versus lift coefficient. As we can see in the right-hand side graph, for the CL alpha graph, the highest airfoil, the highest lift coefficient is for the airfoil lift coefficient, and then followed by the wing lift coefficient, and then the whole aircraft coefficient for the cruise condition. For the takeoff configuration, the lift coefficient is higher than the cruise condition, and then in the landing condition, the lift coefficient also higher. And then these are the polar estimation. For the whole aircraft drag estimation, we use .com software, but for the .com software of the initial whole aircraft configuration was still without the landing gear. So we estimated the landing gear drag using OpenVIP software, and then we use multiplier factor to obtain the whole aircraft drag estimation, including the landing gear drag. And based on the graph, we can obtain the zero lift coefficient of drag. As we can see here in the cruise configuration, the drag power is on the leftmost side with the least drag, and then as the takeoff and landing flap deployed, the drag will be increased as well. And then this the L4D versus CL graph, and for the cruise condition, the L4D is in the region of 10 to 12 L4D at the 0.4 until 0.5 lift coefficient. And then we also present the L4D for takeoff and configuration. If we compare the obtained L4D in this design, the current L4D is higher than the initial sizing. We assume the L4D was 10, but in this design we obtained 11 to 12. And then the next one will be presented by Jerry.
Okay, now for the component weight and the location of the component weight. So on the table, you can see the components of our aircraft, and using the formula from Sadre and Raymer, we can calculate the weight of each component. And after we determining where the component will be located in inside our aircraft, we can determine the CJ location for each axis, X, Y, and Z. And on the right table, you can see the moment of those weight about their center of gravity. Okay, next. Okay, from the table, to this table, we can see that the YCG, the center of gravity on y-axis equals 0. Therefore, we can plot the center of gravity on the XZ plane or from the side view angle. And here are the center of gravity for each component. Okay, next. And to determine the CG range for our aircraft, we give 3 various weight condition scenario, which are empty condition or zero payload, 0 kilogram payload, and then for the max range, or it carry 400 kilogram payload, and maximum payload, which is 1600 kilogram. And from there, we can see clearly that the most forward center of gravity of our aircraft is when it's an empty condition, and the most aft center of gravity is when it carry the maximum range payload, which is 400 kilogram. And on the right side, we can see the plot for our the diagram. Thank you. Next. Okay, this will be explained by Bayu.
Okay, I will explain about the structural design concept. as most aircraft, we chose a semi-monocoque construction using skin, frames, and stringers. The material that we wanted to apply to this concept is some composite materials because the fuselage itself needs to be rigid, so composite materials are adequate for this purpose, and it is also far more lightweight than aluminum. The wing fuselage joint uses a bolt joint because it offers the best, I guess, resistance to fatigue, and also it offers ease of maintenance because it can be the wing can be detached from the fuselage quite easily. Next. This is the structural layout of our fuselage. I revert it from Roscom Part 3. It is given a value for frame spacing and also long range spacing for a small commercial aircraft. And from these values, we can figure out the number of frames and also longerons that we need to apply for our aircraft, which is 18 for the number of frames and also 20 for the number of longerons. Roscom also gave value for the frame depth, which is at 1.5 inches.
Next, for the wing, based on the book by Jan Roscom, for the wing, we will use two spars, one at 15% chord and 65% chord. You would have 15 ribs. This is calculated by the fact that we chose the 24-inch spacings between the ribs. There were a lot of choices between the spacings. There were choices between fighter airplanes or commercial airplanes or transport airplanes. The one that is suitable for this airplane is 24-inch. And the stringers will have 20 centimeter spacings, and there will be 16 of them. The wing will be made out of aluminium because it is sufficient to handle the loads during flight and is also cost efficient. And for the horizontal tailplane, I also took a reference from the book by Jan Roscom. There will be two spars, one is at 15% and one is 70%. There will be 4 ribs with 24-inch spacings as well, and also 11 stringers with 12 centimeter spacings. Yeah, that's all.